Hey, good morning, everybody. What's up? Hope everyone is doing okay today. I'm a little tired this morning, but we'll get through it. So today, it's actually a short lesson today. I don't want to go into the next topic until tomorrow. So it's actually kind of a short lecture today. And a lot of it's review, a little bit's new. So we're going to start with what's called dipole moments. And when we're talking about dipole moments, we're really talking about bond polarity. So in covalent compounds, where electrons are shared unequally, a dipole moment will occur. When this dipole moment occurs, one end of the bond will be slightly negative. We use this weird sign like this. And the other end will be slightly positive. And we use that. So really what we're using is electronegativity difference. The larger the electronegativity difference, the greater the dipole moment. All right, so let's look at some of these. So let's start with, let's start with hydrogen, H2. So in hydrogen, it's sharing these two electrons. Okay, so this is a covalent bond. It's a single covalent bond. All right, but if we do electronegativity difference, 2.1 minus 2.1 is 0. So this is a nonpolar bond. So that means there are no dipole moments. Okay, these electrons are equally shared. Okay, in other words, they're not pulled one way or the other. Okay, so half the time they're over here, half the time they're over here, so we get this equal bond. Okay. Well, what if we look at like the bond in ammonia? Okay, so look at this guy. Okay, now we're talking about this bond specifically right here, or we're talking about this bond specifically right here. Okay, so we're talking about what's happening between two of the atoms. So in the NH bond, again, it's a single pair of electrons. Right? If we look up electronegativities, we get nitrogen is 3.0, hydrogen is 2.1, so we get a 0.9 difference. So this is a polar covalent bond. Okay. In other words, we are going to have dipole moments. Now, what does that mean? Well, really what that means is the electrons are found on one of the atoms more toward one of the atoms than the other. And they're pulled towards the ones that's more electronegative. So the electrons in this bond are going to be pulled this way. They're going to be pulled towards this nitrogen. So that means the end of this bond, the nitrogen end, is going to be slightly negative, and the hydrogen is going to be slightly positive, because the electrons are found more often near nitrogen than they are near hydrogen. So you get this slight negative charge and slight positive charge on the opposite sides of the bond. Okay, and that's what that dipole moment is. So in this bond right here, okay, which is what we just showed, these electrons that are being shared are going to be pulled towards the nitrogen. So this end of the bond up here is going to be slightly negative. This end of the bond over here is going to be slightly positive. That's true of this bond also, and it's also true of this bond. Okay, so when we're talking about dipole moments or bond polarity, we're talking about what's happening with the sharing of the electrons between two of the atoms. Okay. Well, I don't know. How about we look at this one? Carbon dioxide. So I want to look at this bond right here, and I want to know what polarity. Does it have dipole moments? Well, if we look up the electronegativities, we got 3.4, 2.6. And again, this one's 3.4. All right, so we got a 0.8. So this is a polar bond. These 4 electrons are going to be pulled that way. So this end is going to become slightly negative, and this end is going to be slightly positive. Same thing happens here. The electrons are going to be pulled out towards the oxygen, so this becomes slightly negative, okay, and this carbon is slightly positive. But when we're talking about these dipole moments or bond polarity, we're talking about what's happening just between two of the atoms. Now, this plays an important role in what's called molecular polarity. This is bond polarity, okay? And bond polarity is an important part of molecular polarity, but they are different. So let's talk about molecular polarity. Now, when we're talking about molecular polarity, okay, we want to know if the whole molecule is polar or nonpolar. So let's look at water. Okay, here's our water molecule. If I'm talking about bond polarity, which is what dipole moments, we're talking about specifically what's happening between the oxygen and the hydrogen. All right. So if we're talking about dipole moments or bond polarity, okay, we know that oxygen's electronegativity is much higher than hydrogen's. So the electrons are going to be pulled up. They're going to be pulled towards this oxygen. So this oxygen becomes slightly negative, and this hydrogen becomes slightly positive. Okay, so here we're talking about bond polarity. We could do the same thing over here and talk about this bond's polarity between oxygen and hydrogen, and it does the same thing. When we're talking about molecular polarity, now we're talking about the whole molecule. What's happening overall? Okay, is one side positive and one side negative? Or is the whole thing got an equal charge distribution? Okay, or maybe there isn't any charge at all. All right, so when we talk about molecular polarity, we're talking about the whole thing. When we're talking about bond polarity, we're only talking about part of the molecule. Okay, so if the whole molecule is polar or nonpolar, do the ends of the molecule have a charge? That's what we're looking for. So here's a couple things that we can use to do this. Number one, a molecule that is symmetrical is nonpolar. Okay, so if it's completely symmetrical, what that's telling us is the charge is distributed equally across the molecule. And I'll show you that. Asymmetrical molecules are polar molecules if they have polar bonds. A molecule with more than one type of atom attached to the central atom is, let's just say, often asymmetrical, which makes it a polar molecule. A central atom with non-bonding electron pairs is also often asymmetrical, which means it's going to be a polar molecule. If the molecule only has non-polar bonds, it must be a non-polar molecule. So those are some rules that we can use to figure out molecular polarity. So let's look at some things. So let's go right back to our hydrogen, or diatemp hydrogen. Remember, if we're talking about bond polarity, we're saying, hey, look at this is a non-polar bond. The electrons are shared equally. Okay, so this has a non-polar bond. Okay. So this is bond polarity. What about molecular polarity? Is this molecule polar or nonpolar? In other words, is this end positive and is this end negative? Do the ends have opposite charge? Do they have poles? Well, in this case, if the electrons are shared equally, okay, there is no slight negative end or slight positive end. So this would be a non-polar molecule. Okay, let's look at water. Now, so remember, this has two non-bonding pairs on top of it. Okay, it's got two non-bonding pairs. If we're talking about bond polarity, now we're talking about what's happening here. Right? So we know that the electrons are pulled up here towards oxygen. So we have polar bonds. Now, once you have polar bonds, this could be a polar molecule. It could be. If one end of the molecule is negative and one end is positive, you're going to have a polar molecule. Now, okay, we can look at symmetry also. So this thing, if we split it right here, if we split the molecule that way, bring it down a little bit. So if we cut it in half this way, we know that the electrons are pulled towards oxygen. So this end up here, or this side, gets a slight negative charge. What happens to this side of the molecule? Well, it's slightly positive. So this side of the molecule up here becomes negative. This side down here becomes positive. So the molecular polarity would be a polar molecule. Now, like we said before, okay, central atom with non-bonding pairs, and this has two of them, is often asymmetric, and this one is, okay, and it's going to give us that polar molecule. Okay. Now, you got to get this straight, okay? Whether we're talking about bond polarity or dipole moments or molecular polarity, where we're talking about the whole thing. All right, let's look at ammonia, NH3. Do it this way. Yep, I can. So NH3 looks like this. Now, if we're talking about bond polarity dipole moments, and now we're talking about this, okay, we know by electronegativity difference that the electrons are pulled up. Okay, so the electrons are being pulled towards the nitrogen. So these are polar bonds. Okay, so these are polar bonds. What about molecular polarity? Well, okay, this thing has got these two extra pairs of electrons sitting right up here. Okay, we got these two extra pairs of electrons, right? And those electrons push or repel these other bonds. So now this becomes asymmetric, and it's kind of hard to see, but I'm going to see if I can. What if we cut it here? Do it that way. Can you see? Okay. If we cut it here, just like we did with water, okay, this side becomes slightly negative. These guys are slightly positive. That makes this a polar molecule. Okay, so this side, if we look at this model, since our electrons are being pulled up here towards nitrogen, this end becomes slightly negative, and this side down here is going to become slightly positive, which makes ammonia a polar molecule. All right. Let's look at this guy. So now, my question would be, okay, is this a polar molecule or a non-polar molecule? So let's say that this is sulfur and hydrogen, say. Would that work? Oops. Sure. So we have polar bonds. Okay, the electrons are pulled here towards this central atom. All right, so we have polar bonds. Is this a polar molecule? Okay, well, if we look at this, everything's pulled here towards the central atom. So this becomes slightly negative, and then all around it, we have these slightly positives. But this thing, this trigonal planar, is symmetric. Okay? It's symmetric in every way. If we cut it here, it's the same. Right? We can cut it here, it's the same. We can cut it here, it's the same. We could turn it up on end, it's the same. All right? So the charge distribution for this guy is equal. Okay? It's equal. So this would be called a nonpolar molecule. It's got polar bonds, but it's a nonpolar molecule. Now, what if I did this to it? This is still trigonal planar. This is still trigonal planar, but now what I've done is I've exchanged one of the hydrogens for an oxygen. All right, so no longer do we have that equal charge distribution. All right, so no longer is it really symmetric. Okay, this becomes asymmetric. And we're going to end up with a polar molecule with electrons being pulled towards the oxygen. Okay, so this side up here would become slightly negative. This side down here would become slightly positive. And this would be a polar molecule. Let's look at methane. So if we look at methane, okay, this is a tetrahedral. So this is, it may not look it, but it is completely symmetric. Okay, this is a symmetric molecule. Right? So if you look at it this way, we can cut it here, and it's the same on both sides. Okay, we can cut it here, and it's the same on both sides. Okay, and there's actually a third plane that we can cut it. All right, so this is symmetric. If you have a tetrahedral and all of the outside is the same, okay, if all of the outer ones are the same, this is going to be a nonpolar molecule. So if all the bonded atoms are the same, the charge distribution is equal. Okay, so now we can't say that this side of the molecule over here is negative, this side is positive. We can't say that. It's got this equal charge distribution. Okay, so tetrahedrals with all the same on the outside, no matter what, are non-polar molecules. Now, what if I do this, though? What if I take the hydrogen off and I put, I don't know, this would be bromine. Well, this no longer is symmetrical. It's asymmetrical. Okay, so if we look at it this way, electrons are going to be pulled up here towards the bromine. So that means the bromine is going to become slightly negative. All right, so the electrons are all going to be pulled towards the bromine. So this end is going to become slightly positive. Okay, so as soon as we change one, okay, as soon as we change one of them, this becomes a polar molecule. Now, if we change two of them, it would also be polar. Hold on, I think I have enough of these. So if I change another one of the hydrogens to a bromine, it's still polar. Because in this case, the electrons are going to be pulled up towards these guys. So this side of the molecule is slightly negative. This side is slightly positive. So this is still a polar molecule. If I change three of them, this side is slightly negative. This side is slightly positive. This is a polar molecule. If I put a fourth bromine on, though, this now becomes symmetrical again. We get an equal charge distribution. The whole outside is negative, and the inside is positive. Right? So we don't have negative and positive ends. So we're right back to a nonpolar tetrahedral. Let's look at carbon dioxide again. And I got to build it real quick. So in our carbon dioxide, we have two double bonds. It's linear. There it is. Okay, and we already said that this has polar bonds. So we know that the electrons are pulled out. So this side right here, we know the electrons are pulled towards the oxygen. So this is becoming slightly negative, and this is becoming slightly negative, and this becomes slightly positive. In carbon dioxide, though, we again have this equal charge distribution. In other words, we can't say that one side of the molecule is negative and one side is positive. Okay, the charge is distributed across it, right? So in this carbon dioxide molecule, this is completely symmetrical. If I cut it this way, it's the same. If I cut it this way, it's the same. And then if I turn this molecule and cut it this way, it's all the same. So this molecule is symmetrical, right? So this actually has polar bonds, but is a non-polar molecule. Okay. Carbon dioxide pops up quite a bit. How about an octahedral? Okay. What about octahedrals? What do you think? Well, if they're all the same charge, no, not the same charge. If they're all the same atom, okay, we're going to get, again, just like the tetrahedral, we're going to have this equal charge distribution, right? So the octahedral itself is going to be nonpolar. Well, what if I change one of these? What if I take this guy off and put this guy on? So now I've become asymmetric. In this case, the electrons are going to be pulled towards this fluorine side, okay, and away from this hydrogen. So this fluorine side over here is going to have a negative charge. This hydrogen side is going to have a positive charge. So we end up with a polar molecule. Well, what if we have like SF6, SF5, where we got this pair of electrons sitting here? Well, this thing is now, since we have this pair of this non-bonding pair, right? This is becoming asymmetrical, right? We're going to end up getting a polar molecule again, right? So that's okay, some of those crazy shapes that we can get. Take another one off, get this seesaw. Okay, we've got these bonding pairs. This is asymmetrical. We're probably going to be a polar molecule again. Okay, so now you need to be able to look at these molecules and decide bond polarity, so dipole moments between two atoms, and then you need to be look at the whole thing and figure out molecular polarity. Good. I hope the models helped a little bit. The last thing we're going to talk about today is bond order. And it's something we have to calculate. So bond order is the average number of bonds per atom covalently bonded to a central atom. So our bond order indicates the number of bonds in a molecule. And the bond order will give us some information. The higher the bond order, so the larger the bond order is, the stronger the bonds. Also, higher the bond order, the shorter the bonds are. We actually can already know this, all right? So the stronger the bond is, we know that pulls those atoms closer together, and it gives us shorter bonds, but this is also shown in our bond orders. Number 5, it can be a fraction. And that kind of gives us an indication of something else that we'll talk about in a minute. If you calculate a bond order of 0, that means the bonds are not stable. If somehow you get this bond order of 0, that means that molecule is not going to form. Those bonds are not going to form, so it's not going to happen. So how do we actually calculate this? That's our number 7. So what we're going to do is we're going to find the number of bonds coming off the central atom and divide by the number of atoms off the central atom. Okay, so we count the number of bonds coming off the central atom, and then divide it by the number of atoms off the central atom. It's easy. Okay, so let's try it. So let's start by looking at the diatomics, I guess. So let's look at, I don't know, diatomic fluorine. It really doesn't have a central atom, all right? So we're going to have to focus on one of them. Okay, so let's focus on this guy right here. Right? It will give us this bond order, okay, for fluorine. Right? And we count the number of bonds that are coming off of it. So we have one bond. We have one atom coming off of it. Okay, so that tells us that we have a bond order of 1. Okay, a bond order of 1 is telling us that it's a single bond. Which is what it is. All right, let's look at O2. Oxygen actually has a double bond between it. And again, it doesn't really have a central atom, so let's just focus on this guy right here. All right, so now, if it's got a double bond, it's a double bond, we count that as 2 bonds. Okay, so the double bond, okay, is 2 pairs of electrons. Okay, so we're going to count it as 2 bonds. Okay, it's got this has a sigma bond and a pi bond. Okay, so we got a sigma bond and a pi bond happening here. All right. Is that true? Yeah, that's probably true. Okay, now we only have one atom. So if we do that, we get a bond order of 2. A bond order of 2 is telling us that it's a double bond. What if we look at diatomic nitrogen? Triple bond is treated as 3 bonds. Okay, this triple bond is treated as 3 bonds, sigma 2 pi's. Okay, so in this case, we have 3 bonds. We got 1 atom. So we get a bond order of 3. Okay, that bond order of 3 is telling us that we have a triple bond. All right, well, what if we have something other than diatomics? So what if we're dealing with molecules? Well, it doesn't change anything. Okay, let's look at pH 3. Phosphorus is my central atom. Okay, I have 3 bonds coming off of it. I have 3 atoms. So I get a bond order of 1. Okay, which is telling me that these are going to be single bonds, which they are. How about CO2? Again, we're looking at this central atom. All right, so if we look at this central atom, it's got 2 double bonds. Okay, so this counts This double bond counts for 2. This one counts for 2. So this has 4 bonds. It only has 2 atoms. And it gives us a bond order of 2, which is saying, hey, look at these are double bonds. Well, let's look at NO3 minus. Right, so we're going to focus on this nitrogen right here. So if we look at nitrogen, it has 1, 2, 3, 4 bonds, but it only has 3 atoms. We end up with a bond order of 1.33, 1 1/3. Well, what is that telling me? What is that bond order telling me? Well, what it's telling me is that around this central atom, I really don't have single bonds, and I don't have double bonds. I have something in between a single and a double. In other words, we're probably seeing resonance. Okay, that's what it's telling me. This fraction is telling me, look at these bonds really are not a single and a double, or 2 singles and a double. Okay, it's probably somewhere in between that single and double bond. That's what this fraction is giving me. Okay? And it tells us that we probably have resonance. This is called bond order. All right, that's where we're going to stop for today. We have one more lecture, actually, in chapter 9 we're working in. So we have to talk about molecular orbital theory. All right, that will be our last lecture. All right, so have a good afternoon, and we will see you soon.